So a relatively tall column over the ocean, relatively short column over land. Now with all of that said, let's talk for a few minutes about the pressure gradient force. So the pressure gradient force is the force that moves wind from high pressure to low pressure. Make sure you remember that. Winds blow from high to low. And the strength of this pressure gradient force determines how strong the wind is. If you have a strong pressure gradient, you're going to have a fast-moving wind. You're going to have the kind of winds that rip roofs off of houses. On the other hand, if you have a very weak pressure gradient, that's going to result in a relatively weak wind. In this case, you're just going to have a gentle breeze. So that's really what makes the difference between a really fast, windy day versus just a gentle, breezy day. Well, what determines how strong the pressure gradient force is? There are two key things. So let's suppose you have an area of high pressure and an area of low pressure, like you see on this map. Oops, sorry. So let's say you have this map here and you have an area of high pressure and an area of low pressure. We already know that the net force is blowing from high pressure to low pressure. If no other forces are acting on this wind, it's just going to travel from high pressure to low pressure. All right? But what determines how fast it's going to go? Well, the two things are the difference between the high pressure and low pressure. So how high is this high pressure versus how low is this low pressure? If the difference between the two is very small, that means a very small amount of air is going to travel between the two. That represents a relatively weak wind. On the other hand, I'll go back to that in a second. On the other hand, if the difference between the two is really large, that means a lot of air is going to be traveling over. That represents a really fast wind. The other thing is the distance between the two. If the high pressure and the low pressure are really close to each other, that's going to represent a stronger pressure gradient and therefore a faster wind. This can actually be illustrated very easily in hurricanes. Hurricanes represent a really deep area of low pressure, and it's usually a very isolated area of low pressure. The pressure around the hurricane is much higher. So you have this really short distance, and therefore you have a really strong wind. Well, there's actually an equation that we can use to calculate the pressure gradient. And the pressure gradient is simply the difference divided by the distance. So here we have a map, and there are two isobars and 2 points. Point 1 is on the 1020 millibar isobar. Point 2 is on the 1016 millibar isobar. Well, how can we calculate the pressure gradient force? And the 2 points are 100 kilometers apart. How can we calculate the pressure gradient force? Well, if we use this equation, difference over distance, the difference between the two is 1020 minus 1016. What's the difference between those two? Well, it's 4 millibars. Don't believe me? Subtract. So subtract the smaller one from the larger one. 1020 minus 1016 equals 4. And then what about the distance? The distance between the two is 100 kilometers. So to calculate the pressure gradient force, you simply take the difference, that 4 millibars, and divide it by the distance. And that is 100 kilometers. And if you were to punch this number into your calculator, 4 divided by 100, that would equal 4 over 100, which would equal 2 over 50, which would equal 1 over 25. I'm not going to make you reduce fractions, but if you punch those two numbers into the calculator, 4 divided by 100, you would get 0.04 millibars per kilometer. And what this means is that as you're traveling, the air pressure is changing 0.04 millibars for every kilometer you travel. For every kilometer you travel. Let's do a few more examples. So let's say I have two stations, Station A and Station B. Let's suppose that they're 50 kilometers apart. Station A has a surface pressure of 1,004 millibars. Station B has a surface pressure of 1,006 millibars. What is their pressure gradient? I'd recommend taking a moment right now, pausing it, punching in those numbers, and see what you get. Alright, now I assume that you've done that, you've paused it, and now we're back. So how would you do this? Well, the first thing you'd want to do is you'd want to calculate the difference. The difference in this case is 1,006, that's the higher pressure, minus 1,004, that's the lower pressure, 2 millibars. The next thing you'd want to do is determine the distance. Well, I say it right here. Stations A and B are 50 kilometers apart. Finally, the pressure gradient is simply 2 divided by 50, or 0.04 millibars per kilometer. It's literally the same thing as the previous example, just now instead of 4 over 100, it's 2 over 50, but it's the same thing. All right, if you got that one, you're in good shape. If you didn't, let's try another one. So now stations A and B are still 50 kilometers apart, but now station A has a surface pressure of 1,004, station B has a surface pressure of 1,008. How would you calculate this pressure gradient? Again, pause the video, try it yourself, and then let's see what you got. All right, so now let's do it. So the difference, instead of it being 1,006 minus 1,004, it's 1,008 minus 1,004. That's 4 millibars. The distance was the same, 50 kilometers. So the pressure gradient, which is a difference divided by distance, is 4 over 50, or 0.08 millibars per kilometer. The difference doubled in this case. Therefore, the overall pressure gradient doubled. Now, what would happen if instead of changing the difference, we changed the distance? So now let's suppose that stations A and B are 100 kilometers apart. Station A has 1,004 millibars, station B has 1,006 millibars. So the difference stays the same as in example 1, but now the distance has doubled. Well, in this case, you now have a larger denominator. And so you have 2 over 100, which would be 0.02 millibars per kilometer. Well, the reason why this happens is you now have double the distance. You kept the difference the same, but you doubled the distance. So just in summary, if you increase the difference between high and low, that creates a higher pressure gradient force. On the other hand, if you increase the distance, that lowers the pressure gradient force. Now, let's talk about how to do this qualitatively. So we just did a few simple calculations. Now let's talk about how to do it simply by looking at a map. So here we have a simplified map over here. There's a high pressure system at the middle, and then we have these isobars. If you don't remember what these were, we discussed them in the previous lecture. They're just lines of constant pressure. Well, if you notice, wherever the isobars are close together, this represents a large change in pressure over a relatively small distance. That represents a faster moving wind. Winds are stronger when isobars are close together. On the other hand, winds are weaker when they're further apart. That represents a small difference over a larger distance. So on a weather map, if you wanted to identify where the winds are the strongest, look for where these isobars, these lines, are closer together, where they're tightly packed. Wherever they're further apart, that represents weaker winds. Let's do an example. So here is Hurricane Katrina. This was one of the strongest hurricanes on record. It was a major natural disaster, and this image right here shows a pressure map of Hurricane Katrina. Where are the winds in this hurricane the strongest? Are they stronger on the outside of the storm or closer to the center? Well, if you actually notice, the closer you get to the center, the closer the lines become to each other. These are actually where the winds are the strongest. It's where they're closest together. On the other hand, as you travel outside of the storm, the isobars become further and further apart. These represent areas of weaker winds. And so with hurricanes, winds are the strongest closer to the center because the isobars are very close to each other. Now, ironically, the center of the hurricane, the eye of the hurricane, winds are actually very, very calm. It's actually the area around the center, right near the center, called the eye wall, where the winds are the strongest. We'll talk more about that when we talk about hurricanes. Here's one more example. This is Hurricane Sandy. This was a relatively recent and relatively infamous storm. And if you take a look here, let's look near the center of low pressure. So here's the center of low pressure right here. What side of the low pressure would the winds be the strongest? If you take a look, you don't really have a rotationally symmetrical storm. Up here, the isobars are further apart. Down here, they're much closer together. Well, what you actually will notice is where they're closer together is where the winds are typically the strongest. And you can actually verify this. If you take a look at the areas over here and over here, where the isobar lines are further apart, if you take a look at the wind feathers from the station models, remember those were from Module 1, there are fewer feathers on the station module lines, or on these wind barbs. That represents weaker winds, whereas down here, where the isobars are closer together, you actually see stronger winds on this side of the storm. Now, pressure gradient isn't necessarily the only thing that affects the winds here. The forward motion of the storm also plays a big role. There's a few other things that play a big role, but we're not going to worry about that right now. Let's just stress about where these lines are closest together. Right here is where the strongest winds are. The last thing I'm going to talk about in this lecture is another interesting fact about the pressure gradient force. So, we know that air pressure decreases as you rise in the atmosphere. So in a real sense, we have high pressure at the surface, lower pressure aloft. Well, since we've been talking about all this pressure gradient force, shouldn't winds travel from the high pressure at the surface to the lower pressure aloft? Shouldn't winds travel up that way? Well, the pressure gradient force does push wind up that way. However, there is a net force of 0. And the reason why there's a net force of 0 is because as the wind is being pushed up, as that air is being pushed up by the pressure gradient force, it's actually being pushed back down by gravity. And this creates a nifty, convenient little feature called hydrostatic balance. In the case of hydrostatic balance, the upward pressure gradient force is counteracted. It is balanced out by gravity. And so the net vertical force on a parcel of air is 0. Hence, we don't worry too much about vertical winds. and we're not going to really worry about them in this class. Now, this is an approximation beyond the scope of this class. There actually is some vertical motion. There is rising air, sinking air, and so on. But we're not going to really worry about that in this case. In this case, the upward pressure gradient force that would push air up is canceled out by downward gravity. And so everything in this case is balanced. The net force equals 0, and parcels of air aren't being pushed up by the pressure gradient force. Otherwise, Earth would be just one giant vacuum and everything would just float away. That would not be good. So, yay gravity, everything keeps us here near the surface. Otherwise, the pressure gradient force would quickly cause things to float away. So, next time you step outside and you take a deep breath of air, think gravity. That's it for this lecture. In the next lecture, we're going to talk about, once the pressure gradient force begins to accelerate the wind, what other forces act on the wind. So that'll be the next lecture, and that's going to talk about the Coriolis force and friction and the other things that affect the wind. So that'll be in the next